Good morning. So today's topic will be MOS technology, as you know, metal oxide semiconductor FET technology. We have discussed briefly the bipolar technology, its positive and negative features in the last class, of course very briefly. And today I want to cover the MOS technology. I have already pointed out that MOS is superior to bipolar in the sense that it has a natural advantage of very high packing density. So one can realize the LSI and Vlsi circuits with much more, with greater comfort, more comfortably and more easily using MOS technology. And today the MOS technology has advanced to such an extent that one has achieved almost everything so far as VLSI and quite high speed is concerned. As you are aware of that even today's latest Pentium chip, which has been announced at a clock of 180 megahertz, a fantastic development, a single chip computer, fantastic capability. So you see the advantage, and there the MOS technology has played a key role. And by today, by MOS technology, we normally mean CMOS technology. But as you know, the MOS evolved from the single channel MOSFETs, P MOSFET, P channel MOSFET, and N channel MOSFET. So I shall briefly discuss about some technological features of the MOS technology. Let me first draw a cross section of as I told you, that a single inverter of a MOSFET, which I am showing horizontally like this for the convenience. This is, of course, I have drawn just because of that practical difficulty. I have drawn it like this, but usually the circuits are drawn vertically. Here you know that this transistor is called driver transistor of an inverter. The basic inverter circuit. This is a basic inverter circuit. I have discussed about the basic inverter circuit using the bipolar study in the last class. Today's one is a basic inverter. Again, can be equated with the hydrogen atom. It consists of one driver transistor, another load transistor. So this is called driver, and this is called load. We also call it pull down transistor, and this is called pull up transistor. Driver, load, or pull down, pull up. Okay, and from input-output compatibility point of view, the driver transistor must always be an enhancement mode device. This is very important. This must be an enhancement mode. Driver must be the enhancement mode transistor, Why? That to satisfy input output compatibility. This is a very important requirement. On the other hand, the load transistor, which is called pull-up transistor, may be in an enhancement mode transistor or a depletion mode MOSFET, either of the two. The load must be an enhancement mode or a depletion mode transistor. I think you know that the symbol for an enhancement mode transistor is something like this, as indicated here. Whereas for the depletion mode, normally we use a symbol like this. This is for enhancement mode transistor. This is depletion. And normally, if we put a circle here or here, it means PMOS. If I do not put a circle, a small dot here, then it refers to an NMOS. That's the usual. There are many symbols for MOSFETs, but this is a very useful symbol used nowadays. If you just draw it like this, it indicates an enhancement mode N-channel MOSFET, N-MOSFET. Enhancement. Whereas if I put a circle here, it becomes symbolically a PMOS, enhancement mode. If I have two lines here in the channel, then it represents an enhancement mode, a depletion mode NMOS. And again, putting a circle here, it indicates a depletion mode PMOS. That's the usual nomenclature we shall be following. And I told you that the driver load transistor may be either enhancement mode NMOS or PMOS, depending on the technology. If it is an NMOS technology, both the transistors are NMOS. While if it is a PMOS technology, both the transistors are PMOS. Whereas in a CMOS, one of them is NMOS, the other of them is PMOS. It is a combination. That is why it is called complementary symmetric MOSFET. In a CMOS, one transistor is NMOS, the other transistor is PMOS. Now, so to realize the inverter using the MOS, and that is a basic building block for any digital integrated circuit, there are many configurations available. For example, here, whatever I have shown, I have drawn it in such a way that both the transistors are enhancement mode devices, and I have used two power supplies. You see that one is VDD for the drain supply of the chain, the other is VGG, gate supply of the driver transistor. At the input, the gate of the load gate supply of the load transistor, Whereas at the gate of the driver transistor, we apply the input voltage, and from the collector of the driver, we get the output. Okay. Now, it depends how we are keeping this particular device. If you maintain this device, that load in saturation for the entire cycle of operation, then it is normally called an enhancement NELS. The symbol NELS is used for that. That means enhancement mode, N-channel, enhancement mode load in saturation. So the diagram which I have drawn refers to any LS inverter. Means it's an inverter, it's an NMOS inverter which uses an that enhancement mode load in saturation. Of course, for that, usually we short circuit the two. That is a normal configuration. We don't use that VGG. It is eliminated. It is eliminated. If you short circuit the drain and gate, it ensures that the transistor will remain in saturation for the entire voltage cycle. On the other hand, if you apply a separate VGG and you maintain a certain condition that VGG minus VDD is more than VT, the threshold voltage of this transistor, if VGG minus VDD is more than the threshold voltage of this transistor, then we keep it in the linear region or non-saturation region, sometimes also called triode region. So please repeat, I am repeating. If we use two power supplies, all right, and we maintain a condition where VGG and VDD, the difference between the two is more than the threshold voltage of this load MOSFET, then we ensure that this transistor will remain in non-saturation or linear or triode region for the entire cycle of operation. In that case, such a configuration is usually referred to as NELT. Instead of S, we use T. T means triode region. Triode means the initial linear or non-saturation region is also called triode region. Why triode? Because the triode characteristic, the valve triode, you remember, the vacuum tube triode has got similar characteristics. That is why initially the name triode region was given in the very early phase. It is called NELT configuration. So the particular figure which I have drawn, where the gate of the load is shorted with the drain of the load, is called an NELS inverter. All right? Then comes the other type of inverter, which is called HMOS, which was introduced first by several companies, but the HMOS trademark was given by Intel. HMOS means, HMOS, I am writing HMOS, where the first letter H stands for high performance. The first letter H, the high performance MOS. Intel gave that particular nomenclature, introduced a particular nomenclature. What is that? In that case, of course, several other companies also had their product, but HMOS name was given by Intel. So you don't assume that the entire credit goes to Intel. Many companies have the same product, but they did not give the name HMOS. Now, how can you have a higher performance MOS inverter than the kind of things which I have discussed? How do you quantify the performance of a MOS inverter? One is definitely the noise margins, because the voltage levels is at the 5 volt starting. All technology started, digital technology started with, most digital technology started with 5 volts, simply because TTL was an established technology and it was using 5 volt supply. So all MOSFETs, MOS inverters and subsequent digital circuits were developed with 5 volt supply. That was the initial motto. So 5 volt, etc., that is standard. But then you have to maintain a high noise margins for both the, that is called the 0 end and 1 end. That means high end and low end. That is one requirement. And second requirement is high speed. And the third requirement is low power. We should have good noise margins so that it can handle wider signal variations. Second is very high speed, as high as possible. In terms of, we define a quantity called propagation delay, as you know, and then low power consumption. All right? So the MOS inverter, people were trying innovatively how to improve upon all these three things simultaneously. And it was found that there are problems with either NELS or NELT, particularly when you consider noise margins. And another thing I forgot to tell, that is packing density. At the same time, we have to have our inverters small in size so that we can pack many such inverters in a chip. So high packing density. Of course, that is a very fundamental aim which I should have mentioned earlier. That's very important aim. And what people did is, they were trying to investigate the different kinds of inverters available in MOS circuitry and optimize which one is best from every point of view, whatever I have said. Three things as well as packing density. It was found there are limitations with NELS or NELT. That means if both the transistors are enhancement mode, ultimately there are certain problems. We shall discuss this issue afterwards in some more detail. It was found that if the driver transistor is replaced by a depletion mode MOSFET, which is normally on. Depletion mode MOSFET is a MOSFET, if you apply zero gate bias, zero gate to source bias, then it will remain on. Only by applying an opposite bias at the gate, it can be turned off. And that is what is called a depletion mode MOSFET. And it was found that if this load transistor is replaced by a depletion mode MOSFET, we can achieve many important advantages from the point of view of noise margins, logic swing. Another thing, of course, noise margin and logic swing are related. Noise margin, logic swing, speed, power, as well as packing density. From every point of view, there are a lot of benefits gained if I can replace this load transistor by an enhancement mode, same channel, NMOS. If it is an NMOS technology, both transistors are NMOS, but this one is NMOS depletion mode. In that case, what is done? There is a little change in the circuitry. The gate is permanently shorted with the source. Not like this. You have to just open circuit it here and short circuit the gate of the load with the source. Then it will remain on during the entire cycle because this is a depletion mode device. VGS is 0, but it will remain on. And it was found that from every point of view, there are a lot of benefit achieved simply by replacing this transistor by a depletion mode transistor. And that is why the name given by Intel, high performance MOS, HMOS. We shall discuss this thing a little bit more details afterward. But you know that why this thing was known quite earlier, but you know that it took time for the development. Why? Because technologically, developing a depletion mode transistor and enhancement mode transistor simultaneously together was difficult. Making all enhancement mode devices were easier than two adjacent transistors, one enhancement mode, the other depletion mode, were rather difficult. Technologically in the beginning, in the initial phase of development. However, this technological hurdle was quickly removed, and it was found that the HMOS became the dominant technology during the initial years of 80s, first 5 years of 80s, or last few years of 70s. NMOS, a high performance NMOS, was the technology of the day, that time. It was totally dominated by that. And of course, afterwards, CMOS technology matured, and Intel CMOS is again called HCMOS. I think you have heard of. HCMOS means high performance CMOS. Fortunately, this particular company grew from a very small beginning, but it has now given real warning to the big giants like IBM. IBM is tripping like anything, and Intel is rising like anything because their R&D is excellent. So after this brief introduction, I will now discuss quickly how this how it looks like technologically. I will not go into the details of the technology, but I'll give you a hint how things are done. So whatever I have drawn is the cross section of a typical NMOS inverter. Cross section of a typical NMOS inverter. NMOS inverter cross section. You see that there are two MOSFETs. Is the drain of a load, source of the load, drain of the driver, source of the driver. Okay? Then you see that between the two transistors, the gaps are, you know, that are encroached or encircled by very thick oxide. These oxides are called field oxides, and these are achieved by a process known as oxide isolation. But this oxide isolation is called semi-recessed oxide isolation. Semi-recessed oxide isolation. This one, and this one. These are thick oxides, or called field oxides, circumscribing the different active regions where we have developed our MOSFETs. Here one NMOSFET, the other one. Similarly, we have got an array of NMOSs on the chip, and each NMOS is surrounded by very thick oxide. By very thick, it depends on the technology. But today in Vlsi technology, where the channel length is around, say, 1 micron or less than 1 micron, this oxide thickness is around 3000 angstrom or even 2000 angstrom. But when it started with LSI or large scale integration circuit, the channel length was around 5 to 10 micron. On the end, the thickness of the field oxide was 1 to 1.5 micron. 1000 to 1000 and 10,000 to 10,000, 15,000 angstrom. That was so thick earlier in the LSI days. But now it is VLSI era. Everything has been scaled down. All dimensions, not only horizontal but vertical sizes, vertical dimensions have been scaled down. And the situation is like this. This very thick oxide which surrounds, this is simply to improve the electrical isolation of the MOSFETs. As you know that, I just now told you that the people at the Pentium, that those people, Intel has already announced very advanced Pentium chips with 180 megahertz clock. Imagine, our cyber had around 100 megahertz, that's a big mainframe computer. So you just imagine a single desk computer will have a clock, which is the heart of the whole system, operating at around 180 megahertz. Fantastic, fantastic from the point of view of, and very high packing, 10 million, around 10 million devices in a chip. You just imagine how beautiful, how good the chip is, fully functional chip. And that has been possible because otherwise, if that isolation technology was not improved, it could not have had. So oxide isolation, I do not know what isolation they have used. But so far as the research reports are concerned, people are still using oxide isolation for this kind of chip. But maybe for gigahertz, gigabit type of thing, some other technologies, which I have indicated in some earlier class, SOI and other technologies may be used for the gigabits. But hundreds of megahertz still today, oxide isolation is most popular. Now here one thing you note, the gate of the MOSFET has been realized using polysilicon. Okay? Both the gates, this is a gate material made utilizing polysilicon, usually a doped polysilicon. And the source and drains, naturally because it is NMOS, the substrate is P substrate, P-type substrate, and source and drains must be N plus regions. It must be N plus region, and that is how we define NMOSes. And one thing to note here, that the source and drain edge almost exactly coincides with the edge of the poly gate, polysilicon gate. If I draw a vertical line here, you note that the right edge of the polysilicon gate is coincident with the left edge of the N plus source of the load transistor, and that is true for all other edges, this edge, and this edge. And this is necessary. Do you know why? Again, I have perhaps indicated earlier, if there is an appreciable overlap capacitance between the gate and drain, normally you know that if when you do this thing by diffusion, there is a lot of lateral diffusion, and as a result there must be some overlap of the polysilicon gate over the two diffusions. There will be little overlap to the right this side and to the left this side, but what will be the bad thing out of that? And that will be important if you want enhancement mode MOSFET. This must be ensured that the gate covers the whole channel from one edge to another edge, from source to drain. If it does not cover, that you cannot get the enhancement mode operation. I think you know that. Why? Can any one of you tell me? Why it is important for enhancement mode that the gate must cover the whole channel length from the source to drain diffusion edges for enhancement mode operation. You remember, enhancement mode MOSFET is normally off. It is normally off. When you do not apply any gate voltage, it is off. It is in non-conducting state. Only when you apply appropriate gate voltage, this turns on. Appropriate gate voltage above the threshold voltage, you remember, it turns on. And you remember the physics? Just in the surface below the gate, an inversion layer is formed. This is p-type substrate. So a layer of electrons, if I apply a positive bias here, it will repel holes and attract electrons. And if you apply sufficient positive bias at the gate, there will be a large number of electron sheath, minority carrier charge sheath, electron sheath at the surface, and that is what is known as inversion layer. And this inversion layer connects the source and drain, and you get on state. We say that the transistor is on. In order that inversion layer form over the entire channel from one end to another, the gate must exactly coincide, or rather it should extend from exactly from the source to, there should not be an underlap. That means if the polysilicon gate width is less than the distance between the two diffusions called channel length, then it will not work, because you have to form inversion layer everywhere so that the source and drain connected. Therefore, technology must ensure that. Earlier what was done, we were using ordinary mask alignment process to define the gate after the source drain implantation or source drain formation. And you know, after all, mask alignment is a mechanical thing. You cannot ensure that there will be exact or zero exact thing. So what we are doing is we are always keeping the gate length sufficiently wider than the channel length. The gate length means from here to here, the gate length sufficiently wider than the channel length, so that even after all those registration errors in the aligner, we always ensure that yes, at least the gate covers the whole, gate electrode covers the whole channel from one end. There may be some little overlap, little extensions here and extensions here, but there is no underlap anywhere. This is important for enhancement mode operation of the transistor. And in doing so, what are the drawback? Because particularly between the drain and gate, the capacitance CGS, CGD, that reflects to the input magnified through Miller effect. Remember that if AV is the gain, voltage gain of an inverter stage, it is an inverter, negative voltage gain of an inverter stage, then that bridging capacitance between the drain and gate that reflects to the input magnified. How much magnified? 1 plus AV times CDS. Sorry, 1 plus CGD. 1 plus AV times CGD. And it reduces speed because of RC delay, higher RC delay. Therefore, if you want to improve speed, this overlap capacitances should be minimized. If there is sufficient overlap capacitance, the speed is automatically hampered. So today you can that 180 megahertz this chip could not have been invented if the proper technology was not available. But fortunately, some technology came which is called self-aligning gate formation technology. Self-aligning gate formation technology. What you do normally, after the formation of the thin gate oxide, very thin gate oxide, you know the thing, gate oxide must be very thin and high quality. I have emphasized that earlier. The gate oxide must be very thin and of very high quality. After the formation of the gate oxide, you deposit polysilicon film and pattern it in the form of strips as indicated here. This one, a strip of polysilicon here, a strip of polysilicon here. Then you do a heavy phosphorus implantation. A heavy phosphorus ion implantation. What will happen? Can you tell me? In that case, this polysilicon strip will act as a mask against implantation. This is usually several thousand angstrom thick. Whereas the gate oxide is very thin. What is the thickness? In Vlsi is less than 300 angstrom today. And in LSI it was around 100,000 angstrom. It is very thin. Whereas this one is quite thick, 3,000, 5,000 kind of thickness of the polysilicon, 3,000 to 5,000 angstrom today. So when you do a heavy ion implantation, this region there will be no ion implantation. But from here to this point, from here to here, here to here, and again there is thick oxide here, there cannot be any implantation through the thick oxide. So exactly from this region to this region, you will get heavily doped N plus layer to form your source and drain. And they are self-aligned. Ion implantation being a highly directional process, a beam of ions, highly directional process, these are automatically aligned, and there is a fantastic improvement so far as these capacitances are concerned. And you can always ensure that there will be never underlap. There will be always a little positive overlap, but that will be extremely small. And this was a real good technology since the development of MOSFET, the early 60s. This was a great thing, in the MOS technology. And the speed was automatically improved greatly. And here also we do that. So this is one key feature of the MOS technology. Please remember, it is called self-aligning gate formation technology. The other key feature I have already told you, that is oxide isolation. Oxide isolation, the other key feature I have already mentioned. Third key feature of the technology is the adjustment of threshold voltage. The third key feature, the first key feature is oxide isolation. Second key feature is self-aligning gate formation. These are very important. And the third key feature is threshold voltage adjustment. Why it is so important? You remember that MOSFET operation, its DC voltage levels, etc., is greatly influenced by the threshold voltage. Higher is the threshold voltage, you need larger power supplies for operation. And if any one of you goes through a book called MOS LSI by Carr and Mise, MOS LSI by Carr and Mise. Aerial technology is very nice because it is an old book. You will find that how the technology evolved gradually. And you will find that this threshold voltage, the role of threshold voltage, the adjustment of threshold, how important it is. Initially, it was difficult to make a MOSFET with a threshold voltage less than 3 volt. Then can you use 5 volt power supply in that case? If the threshold voltage is 3 volt, you do think that 5 volt power supply? No. So MOS technology started with a much larger power supply voltages. 12 volt, 15 volt, even 30 volt in the first few years. But you know, that was not compatible with MOS, TTL, and that time dominant thing was TTL. There was always a need an interfacing circuitry, level shifter, between the MOSFET and TTL. And therefore, technology gradually developed how to reduce the value of the threshold voltage. It was a very, very important requirement of the MOS technology was in that time how to adjust, rather reduce the threshold voltage. And it was found that is a very simple trick can do it. What is that? Before the polysilicon deposition for the gate formation, in the channel region, you have a very shallow implant of proper impurity atoms through the same oxide after the gate oxidation, but before the polysilicon gate deposition. So let me repeat, after gate oxidation, but before the polysilicon gate deposition, you have or you apply a very shallow low dose implant of appropriate ions to control threshold voltage. For example, in NMOS, it was found that a low dose, low energy boron ion implant could control the threshold voltage to whatever value you need. That's a great thing. Just a controlled ion implantation of boron ions into the channel region through the gate oxide before polysilicon deposition could adjust the threshold value, voltage value, to any value you desire. Unfortunately, I don't have time to discuss the more details about this technological aspect. But for your information, this is a very important, another key improvement, key feature in MOS technology, and that is what is known as channel implantation. Channel implantation. All right? Then, so you know that your problem was solved. Now I can have any MOSFET with any threshold voltage. So even I can design a MOSFET for 1 volt power supply, which is the demand of the day. It would have been impossible if I did not have that channel implantation concept, which was evolved in 60s. And the last and very important key feature is called a silicide process, salicidation. Salicidation. It means, it stands for self-aligned silicidation. This process is called salicide. S-A-L-I-C-I-D-E. Self-aligned silicide. Self-aligned S-I-L-I, silicide process. You know that you are not interacting with me, but you should have interacted. Why I spoke of polysilicon gate? Though it started as metal gate in the initial days, aluminum gate, the first few years of MOS technology was dominated by aluminum gate, simplest type. But then it was quickly replaced by Initially, tungsten gate, moly gate, and all these things came, but ultimately it was almost universally replaced by polysilicon gate. Can you tell me why?
Because the oxide thickness is very low, and the polysilicon also acts like a contact. Because when we dope it with the impurity atoms, it becomes saturated.
Yeah, no, that is contact. So metal is also tungsten, aluminum. They are also contact materials.
So if we deposit the metal directly on the oxide can get destroyed.
Yeah, that came after. You are right. That because post. That when polysilicon came, that was not the for purpose. Afterward, it was fun. Polysilicon but it's a very acute technological thing. I think you have gone through. That's very good. But the main point was that polysilicon is a high temperature. It can be easily oxidized. But one aluminum has got a melting point around 750 degrees centigrade. And our most processes are carried out above around 1000 degrees centigrade. So once you have aluminum, you just cannot do any high temperature processing. But polysilicon, that was excellent. It can be oxidized. It can be covered by an oxide. So its life is long. It is just silicon, but polycrystalline silicon. It's a great advantage. Thirdly, polysilicon can be doped to any level, whatever you like, just like silicon. You can adjust its work function. So you can control the threshold voltage. This is another advantage. And fourthly, using this polysilicon, when you do the ion implantation, the polysilicon gets also doped for N+. As you said, that polysilicon I am using as a mass against ion implantation for the source DEN formation. I have told you. Then polysilicon also gets doped. It becomes N+, and it's fine. Okay, it serves my purpose. I don't have to do anything. Then I oxidize it, just like silicon. I cover it by oxide wherever I like. And wherever I do not like, I open a window, take contact out of it. And I can use this poly as an interlevel, as a metal interconnect for an interconnect level. Do you follow? And what is the drawback of polysilicon? It's excellent. But drawback is polysilicon sheet resistance or conductivity is not as high as that of metal. So as a interconnect material, polysilicon has a tremendous drawback. You see that in many MOSFET circuits, that the input lines are all gates and they're all poly level. You call it polysilicon level, poly level. And these input lines can be quite long. That today things have shrunk to around a micron or even less. The widths, the line widths are around a micron or even less. And if the polysilicon resistivity can never match that of metal, aluminum or gold, whatever metal you use. So that a long line of poly will give you a lot of resistance. And ultimately you have the RC delay and it reduces the speed of operation. So what is normally done on the polysilicon, we deposit a metal like titanium. And by heat treatment, we convert the polysilicon into it's called titanium silicide, TiSi2. The polysilicon is converted into titanium silicide. And that reduces not only the resistivity, but also ruggedness, and all these good things come out of that. This is called polysilicon getting converted into a silicide of much lower resistivity, which reduces the time delay, the RC time delay, and hence improves the operational speed. Another problem was there that on the contact, when you deposit a metal directly, there are many problems. Spiking, then the contact resistance, etc. When you deposit a metal as indicated directly on the silicon for taking the drain or source contact, what is the problem? One problem is some metal may diffuse through this and short from here directly to the substrate, called spiking problems. That happens. Secondly, the contact resistance may not be very, very low, and that is a very important requirement today. So if you want to have a very low contact resistance and a very sufficient rugged thing so that there is very little interdiffusion, then a layer between metal and silicon is also necessary. Again, that is usually titanium silicide. So if you deposit titanium both on polysilicon and on these windows over silicon simultaneously and silicide it, then you get a lot of advantage ultimately. And people have invented a technique, we'll not go into the details of that, called salicidation technique, by which automatically, you know, that these gaps between, you know, that you see that between this metal and this metal, ultimately this is the gate and this is the drain. But you see, I have intentionally shown a lot of gap because I have to have some gaps. But these gaps, you have to use a mask for that. And mask means that you have to allow sufficient dimensions, you have to give a lot of tolerance, etc. So what has been done by the salicide process, and again, a self-aligned, just like our polysilicon gate formation, another self-aligned formation has come, which automatically shrinks the whole circuit to extremely small size with very, very high order of reliability. So all this packed together, you know, is really the present day Vlsi MOS technology. So today I have discussed NMOS features, key features only, and in the next class, I hope to discuss about the